Welcome! My name is Victoria Winland. Today we'll be learning about how to graph linear inequalities on a Cartesian plane. First, we will review how to graph inequalities on the number line. We will look at the equation 4x minus 12 is less than 8. The first step is to isolate the variable x. And to do this, we will have to add 12 to both sides, and this will give us 4x is less than 20. The next step we'll have to take to isolate our variable is to divide both sides by 4, and this will leave us with our answer, which is x is less than 5. We can graph this function on the number line. Since x is less than 5, we will put a marker on the 5. Notice the circle is open and not closed. This is because x is less than and not equal to 5. If x were equal to 5, then the circle would be closed. Next we will look at which side of the graph to shade. We can plug in a number on each side of the circle to find the solution. For example, 6. 6 is less than 5. This is not a true statement, so we know that those solutions are not true, and we cannot shade that side. Next we can try 4. 4 is less than 5. This is a true statement, and we know to shade the left side of the graph. Moving on to the new concept, which is graphing inequalities on a Cartesian plane. We will look at the inequality 2x plus y is greater than or equal to 5. You will need to treat this inequality as an equation. The first step is to put the equation in slope-intercept form, which is y equals mx plus b. Since there are no like terms to combine, you will simply move the 2x to the other side of the equation. This equation will then become y is greater than or equal to negative 2x plus 5. Now that the equation is in slope-intercept form, we can graph it. We know from our slope-intercept form that the y-intercept is 5. You can then put that on the graph. Our next step is to find our x-intercept. You can do that by replacing the y in the original equation with 0. You always want to use the original equation in case the slope-intercept form is wrong. Our original equation was 2x plus y is greater than or equal to 5. And then this becomes 2x plus 0 is greater than or equal to 5. So we can solve this equation and find that our x-intercept is 5 over 2. And we can graph that as well. And then connect our 2 points. The next step is to shade all the values that make the equation true. When y is greater than, you will shade in all the solutions above the line. When y is less than, you will shade all the solutions below the line. In this equation, y is greater than, so we will shade all the solutions above the line. If you cannot remember this, you can always choose a coordinate pair not on the line to check. For example, the point 0, 0 is always a good point to use. And again, you should always use the original equation just in case the slope-intercept form is wrong. The original equation is 2x plus y is greater than or equal to 5, and the point I suggested to use was 0, 0. So 2 times 0 plus 0 is greater than or equal to 5, and if you solve this, you will find that 0 is greater than or equal to 5. This is a false statement, which means that the point 0, 0 and every other point on this side of the graph is not a solution. Another example we will look at is 4x minus 3y is greater than 6. The y variable needs to be isolated in order to get our slope-intercept form. To do this, you'll need to subtract 4x and move it to the other side of the graph, or the other side of the equation. And this will give us negative 3y is greater than negative 4x plus 6. The next step is to divide the equation by negative 3. And when you divide by a negative number, you will need to switch the direction of your sign. A less than sign will become greater than, and in this case, the greater than sign will become a less than sign. So our slope-intercept form is y is less than 4/3 x minus 2. Now that our inequality is in slope-intercept form, it can be graphed. We know that our y-intercept is -2, and we can solve for our x-intercept by replacing the y with 0. And we know that it is 3/2, and it can be graphed as well. And we can connect our dots. Notice here that this was graphed with a dotted line and not a solid line as the last example was. This is because our inequality sign is less than, but it does not have the equal to sign as well. This is because all the solutions on the line cannot be included. Our next step is to look for all the solutions that can be included either above or below the line. Since y is less than, we will include all the solutions below the line. A special graph you may see is a horizontal graph. An example is y is less than or greater to 4. There is no x value and it is not specified in the equation. It could be anything. The graph will never cross the x-axis, unless of course the graph is on the x-axis, which would mean your inequality would be y is less than 0 or y is greater than 0 or any variation of that. So since the line will not cross the x-axis, you can look at the table I have in the corner. So the x-coordinate could be 0 and y will be 4, or the x-coordinate could be 4 and y will be 4. Or the x-coordinate could be -4 and y will also be 4. Y will always be 4 for this equation, and you can graph accordingly. This graph will be solid because y is less than and equal to 4. And you will need to shade everything that is less than 4, as our inequality has stated. If you cannot remember, you can always use our rule that we stated in a couple slides ago. You can look at the 5 and plug it into the equation. 5 is less than or equal to 4. This is not a true statement, so we know not to shade above the line. We can look at 3. 3 is less than or equal to 4. This is true, so we know to shade everything below our line. Another special graph you may see is a vertical graph, such as x is greater than or equal to -3. There is no y value for this graph. It is not specified and it could be anything. The graph will never cross the y-axis unless, of course, the graph is on the y-axis. Then the example would be x is greater than 0, or x could be less than 0, or any variation of that. Since the line will not cross the y-axis in this example, y can be anything. You can look at the table I have in the corner here. So x can be -3 and y will be 0, or x can be -3 and y could be 4, or x will be -3 and y could be -3. And you can graph accordingly because x will always be -3. This is the only time a graph will never have an above or below because our graph will be a straight line up and down. So we cannot use our rule for shading above or below. So we'll have to use the trick of looking at the numbers next to our original circles. So we can look at our number 4 and our -2. So -4 is less than or is greater than or equal to -3. This is not true. So we can look at our -2. -2 is greater than or equal to -3. This is true, so we know to shade everything to the right of the graph. Thank you for listening, and I hope you found this helpful.